All right, welcome back to what I can only hope are good choices. Mic check 1 2 1 2. That's a good way to start the video. Looks like it's a little bit low, but I guess I'll leave it like that. So got two series going. I've got the automated your network series, the LPIC series. I want to get that LPIC, so I'm going to work on an LPIC video today. Automate your network series is kind of a bit more interesting in my opinion, but um, I don't know. I just kind of feel like I want this certification. All right, so we're on to lesson 103, lesson 2 of 103.7. We finished up lesson 1 in the last video. So we're talking about GNU and Unix commands. I kind of made a mistake in one of my videos at the beginning where I talked about how this is kind of the best of both worlds of open source, products. Well, Unix is not that. Unix is the closed source licensed program that people were trying to get around because they couldn't afford the licenses. So GNU, GNU stands for GNU is not Unix. So GNU probably came first before Linux. I don't know. It's really not that important unless it's on the test. All right, so the objective for this lesson, lesson 2 of 103.7, is to search text files using regular expressions. Okay, so introduction. Streaming data through a chain of piped commands allows for the application of compound filters based on regular expressions. Regular expressions are an important technique used not only in system administration. Something about this looks misspelled to me. It might just be one of those days where, yeah, it's just one of those days where words look funny. Also in data mining and related areas, two commands are specifically suited to manipulate files and text data using regular expressions: grep and sed. Grep is a pattern finder and sed is a stream editor. They are useful by themselves, but it is when working together with other processes that they stand out. Alright, so the pattern finder, grep. One of the most common uses of grep is to facilitate the inspection of long files, using the regular expression as a filter applied to each line. It can be used to show only the lines starting with a certain term. For example, grep can be used to investigate a configuration file for kernel modules, listing only option lines. Okay, so grep. Now here's our grep expression. I think this. Now we learned about globbing. We learned about basic regular expressions. We learned about extended regular expressions. I'm not sure what this is. It's whatever grep wants. So let's take a look at like what the default input is for grep. So we're gonna go to my lab. Then we're gonna type in grep --help. All right, so it's a pattern, and I'm not sure. I'm not sure what this is. If it's a glob, if it's a. So it looks like it's probably a basic. Okay. Here we go. So we see this default here. So pattern is a basic regular expression by default. That's important to know because, as we saw, there's different characters in the regular expression. They do different things. But you can easily just turn it into extended by dash uppercase E. Okay, so the pipe character can be employed to redirect the output of a command directly to grep's input. The following example uses a bracket expression to select lines from fdisk-l output, starting with disk with a capital D space. So that's the yeah, so that's the search string. That's the content. That's the portion of the search of the characters in the search string. Those are the characters in the search string that we want to match against. So we need to use this regular expression right here. And it's a standard regular expression, or sorry, basic regular expression. Well, you could call it standard either, because there's no dash uppercase E to make it extended, or the other kinds of regular expressions that are accepted. So the following example uses a bracket expression to select lines from f-l output starting with that. So starting with, we know what that is. And now we're going to match /SDA or /SDAB. So what we need is a matching group or a character class. I forget exactly what it's called. But we need those open and closed brackets because we want to say if any of those characters within match. And we're not saying to match the string A and B together. We're saying A or B is a valid match. So it's a one character match in the search string, and the character can be either A or B. Alright, so the mere selection of lines with matches may not be appropriate for a particular task, requiring adjustments to grep's behavior through its options. For example, option -c or --count tells grep to show how many lines had matches. So here we go, f-l pipe grep. So now we can just feed grep a -c and just get a count of how many matches there were. So that can be useful, for example, in like a networking context. You just want to know like how many devices there are on your network and see if that matches. So you can just do a -c and save yourself some output. So here it is, -c, print only a count of selected lines per file. The option can be placed before or after the regular expression. Other important grep options are -c or -count, which is the one we saw before. Instead of displaying the search results, only display the total count for how many times a match occurs in any given file. Then -i or -ignore -case. Turn the search case insensitive. So the match string, whether it contains uppercase or lowercase characters, will the regular expression you write does not have to take into account that. It's case insensitive. Okay, and then -f or --file equals, and then you feed it a file for input. So indicate a file containing the regular expression to use. So okay, so let's say you have a really sophisticated long regular expression. You don't have to do grep and then here's my regular expression here. Instead, what you can do is open a file editor or just upload a file up to it. New grep-f, say my regex.txt, whatever it is. And now you kind of spare yourself that output of the screen. Alright, so -n or --line -number. Show the number of the line. That could be a really useful one. If you're searching through a file and you want to see where in that file that match occurred, just throw a -n on there and you'll see that. Next one is -v or --invert -match. Select every line except those containing matches. Then -uppercase H or --with -file name. Print also the name of the file containing the line. Then we've got -z or -null -data. Rather than have grep treat input and output data streams as separate lines using the new line by default, instead take the input or output as a sequence of lines. When combining output from the find command using its -print0 option with the grep command, the -z or -null data option should be used to to process the stream in the same manner. Alright, so although activated by default when multiple file paths are given as input, the option -H is not activated for single files. That may be critical in special situations, like when grep is called directly by find, for instance. So you can, when you do find, you don't have to do like a pipe into grep. You can use this special -exec option, and then you can execute a command based on what you found. So what we're going to do is in here, we're going to search for files. And then for each file we find, we'll execute this case-insensitive regular expression against it. And then we will pipe that into the cut. And then we'll just see the first 100 lines of, first 100 characters of that, I believe. So that may be critical in special situations. There we go. In this example, right here, find lists every file under /user/share/doc, then passes each one to grep, which in turn performs a case-insensitive search for 3D modeling inside the file. The pipe to cut is there just to limit output length to 100 columns. Note, however, that there is no way of knowing from which file the lines came from. This issue is solved by adding -H to grep. And remember what uppercase H does. It prints also the name of the file containing the line. So here we go. Uppercase H is right there. So now we can see the names of the files containing the line. Now it is possible to identify the files where each match was found with that -uppercase H. To make the listing even more informative, leading and trailing lines can be added to lines with matches. So we can do that. Here we go. So here's a probably a leading and trailing line. The option -1 instructs grep to include one line before and one line after when it finds a line with a match. These extra lines are called context lines and are identified in the output by a minus sign after the file name. The same result can be obtained with -uppercase C space 1 or --context equals 1, and other context line quantities may be indicated. There are two complementary programs to grep, egrep and fgrep. The program egrep is equivalent to the command grep-e, which incorporates extra features other than the basic regular expressions. For example, with egrep, it is possible to use extended regular expression features like branching. So we've got egrep here, and now we have an example of an extended of branching, which you can do now that you have extended regular expressions. So we're searching for either modeling or printing. And we've got our capital H, so we got the file names. I thought we did. Oh, here they are right here. I thought there was a I thought there would be just a colon after each file name, but it looks like it's kind of different. Like some have colon, some don't have anything. They just have like a dash. So, oh, you know what? Let me explain this output. So, what we see here is here's the file it was found in. We see that with a colon. Now, okay, well maybe it's not quite that simple. What I was going to say is because we're using this -1, we're seeing the line before it, and the line before it doesn't necessarily have the same syntax, but it's perhaps not quite that simple because here we're actually seeing two lines before it that don't share that similar syntax. So kind of taken off guard by that, but I don't think it's I don't think it's that big of a deal. All right, so in this example, either 3D modeling or 3D printing will match the expression case insensitive to display only the parts of a text stream that match the expression used by egrep. So to display only the parts of a text stream that match the expression used by egrep, use the -O option. The program fgrep is equivalent to grep-uppercase F. That is, it does not parse regular expressions. It is useful in simple searches where the goal is to match a literal expression. Therefore, special characters like the $sign and the dot will be taken literally, not by their meanings in a regular expression. So you can do that with a capital F and make sure that there are no and then you can make every character literal. All right, so next section is the stream editor, SED, and I'll take a break and I'll be right back. All right, welcome back. We're ready to keep going. So the stream editor said, the purpose of the SED program is to modify text-based data in a non-interactive way. It means that all the editing is made by predefined instructions. Okay, that's interesting. Not by arbitrarily typing directly into a text displayed on the screen. In modern terms, SED can be understood as a template parser. Given a text as input, it places custom content at predefined positions or when it finds a match for a regular expression. SED, as the name implies, is well suited for text streamed through pipelines. Its basic syntax is SED-lowercase f and then a script. When editing instructions are stored in the file script or SED-E commands to execute commands directly from the command line. So that's its basic syntax. When editing instructions are stored in the script, you use the -lowercase f. But when you want to execute commands directly from the command line, you need to use a -lowercase e. If neither -lowercase f or -lowercase e are present, SED uses the first non-option parameter as the script file. It is also possible to use a file as the input just by giving its path as an argument to SED. SED instructions are composed of a single character, possibly preceded by an address or followed by one or more options, and are applied to each line at a time. Addresses can be a single line number, a regular expression, or a range of lines. For example, the first line of a text stream can be deleted with 1 lowercase d, where 1 specifies the line where the delete command d will be applied. To clarify SED's usage, take the output of the command factor, and then now these are backticks, so remember what this does. It converts the output of this command to input, and then input can be fed to the command factor, which returns the prime factors for the numbers 1 through 12. So factor space backtick SEQ space 1, 2, and a backtick. So SEQ1, 2 is its own program. Let's demo that here. All right, so the output of SEQ1, 2 is to print out the sequence of every number in the number 12. So 1, 2, 3, all the way up to 12. And that is output. So it's to the standard output. So if we want that to be input, we surround it in backticks. What happens if we do that? See, now we've got command is not found. The input here cannot be accepted. The input. So see what's happening. Let me take a moment here. When this was output, then yeah, it knows what to do with standard output. It displays it to the bash prompt. But now that this is input, what does this error mean? Well, let's start with the first character here, this 1. Where does this look familiar? It's the same right here as the 1. So since this is input, what we're trying to do is we're trying to enter in to the bash prompt input. So the first line of output from SEQ12 is that number 1. So what we're doing when we surround it in backtick is we're doing this. And you can see we get the same message, standard error. 1: command not found. That's because we're trying to enter each line of standard output from that command into something, in this case the bash command prompt, as standard input. And since it's not a valid command, it just stops right there. It doesn't go on and try the other ones. So hopefully that makes sense what we're doing. This line here, backtip SEQ space 12 and backtick, is the exact same thing as doing typing the number 1 and then pushing enter. It's the same thing because you're taking the output, you're converting it to input, and you're passing that to bash. And the output is a sequence of numbers 1 through 12, but since there's an error on that first number, it does not continue with the rest of the numbers. So it's the same thing as typing a 1 and hitting enter. All right, so oops, hold on a second. Let me take a quick break. All right, welcome back. So now we're so if neither -f or -e are present, SED uses the first non-option parameter as the script file. So it always is a file. It doesn't come from input or standard input. It's also possible to use a file as input just by giving the path as an argument, giving its path as an argument to sed. All right, so sed instructions are composed of a single character, possibly preceded by an address or followed by one or more options, and are applied to each line at a time. Addresses can be a single line number, a regular expression, or a range of lines. For example, the first line of a text stream can be deleted with 1D, where 1 specifies... Okay, and we actually read all this. No, we didn't. Where 1 specifies the line where the command delete will be, where the command D will be applied. To clarify SED's usage, take the output of the command factor SEQ10 or SEQ12, which returns the prime factors for numbers 1 through 12. Okay, so yeah, we went through all this. Yep. So now let's move on to now that we know the difference between input and output, which we already kind of knew. Let's run the input, or let's convert the output of the SEQ12 command to input, and then feed it to the command factor. All right, and now we've got so now we've got the prime factors for the numbers 1 through 12. First prime factor for the number 1, it doesn't have one. Then it's 2, 3, 2, 2, 5, 2, 3. So those are all prime numbers. All right, so deleting the first line with SED is accomplished by 1D. Okay, so it's kind of like another utility where you can do like cut, that it's just a more sophisticated way of doing that, I think. So let's try this. So factor, then convert it SEQ12, and then pipe it to pipe the output of factor, convert it to input, and feed it to the SED command, and then we'll provide it the option 1D for delete the first line. And there we go. We've got the same output, but we're missing the first line. A range of lines can be deleted with a separating comma. All right, so let's try that. So it's the same syntax. It's just you can modify this character here before the D, and you can do it by, you can make it into a range by using the comma character. There we go. Now we've got 8 through 12. More than one instruction can be used in the same execution, separated by semicolons. In this case, however, it is important to enclose them with a parenthesis so the semicolon is not interpreted by the shell. So let's try making that mistake. So we're going to do 1D, and then we're going to do semicolon 11D and not wrap it in quotes. Okay, so now we can see we've got this command not found, because what the semicolon does is it says you're finished entering this command. Here's the next command you're entering. So after we finish entering this in, now we enter the other one in as input, and it'd be the same thing as doing this. And you see we get the same message. Okay, so let's wrap it in quotes. And now we get the same answer as in the learning materials. In this example, 2 deletion instructions were executed. First on lines ranging 1 through 7, and then on line 11. So you can notice we've got line 8, 9, 10, and then we're skipping line 11 to line 13. That's because we have this second delete statement. An address can also be a regular expression. Oh, that's interesting. So only lines with a match will be affected by the instruction. So here we go. So now we can make it. So we've still got the 2. So now we're deleting the first line here, but now with this colon here, with this semicolon, now the second part is a regular expression. So remember what the regular expressions are. Oh, you know what? So this has that funky syntax that we saw before. So it's wrapped in these. So that means what's in between those is a regular expression, and then regular expressions have atoms. So the first atom is a semicolon. The second atom is any character. The third atom is, we need to see that prior character specified in the prior atom 0 or more times. Then we're matching on a 2. Then any character again. So we see we have no 2's in our output there. Okay, so an address can also be a regular expression, so only lines with a match will be affected by the instruction. The regular expression, and we can see this is the regular expression. We know that because it's encapsulated in these forward slashes. So that regular expression matches with any occurrence of the number 2 anywhere after a colon, causing the deletion of lines corresponding to numbers with 2 as a factor. With SED, anything placed between slashes is considered a regular expression, and by default all basic RE is supported, and RE stands for regular expressions. For example, SED-E, and then now it gets tricky because here's our regular expression, so it has to begin with a pound sign, and then this is the instruction we want it to delete. So this, for example, here, SED-E, -E stands for, if I remember correctly, -E means you're not giving it a file, you're just giving it right on the command line. So I forget where this is written. Now this is SED, so we need to go down to the, yeah, so -E means you're executing commands directly from the command line. So if we didn't have that -E here, it would think that this was a file name. Okay, so -E, there we go, for the regular expression just being given here and not being given as a file. And then the file that is the search string. The contents of the file will be the search string. And the file is /etc/services. So in this example, it shows the contents of the file /etc/services without the lines beginning with pound sign, the comment lines. The delete instruction D is only one of the many editing instructions provided by SED. Instead of deleting a line, SED can replace it with a given text, which could be pretty nice. So here we go, vector, and then we're piping it into there. So now we're doing C for cut. I don't know what C stands for, but we can see we got the same syntax. We're deleting the first line. Okay, great. Then we're moving on to the next one, which is encapsulated in these forward slashes. So that means that it's a regular expression. And then we're applying the actual command to it, which in this case is C. And C means we're going to replace anything that matches this with this word here removed. There we go. All right, so the instruction C removed simply replaces a line with the text removed, all in uppercase. In the examples case, every line with a substring matching the regular expression :dot star 2 dot star is affected by instruction C removed. Instruction A, uppercase text, copies text indicated by text to start a new line, after which the line with a match. After the line with a match. The instruction R, lowercase r, file, does the same, but copies the contents of the file indicated by file. And these are all alternatives that you could have here after the second slash. So you could have C, which is to replace the line. You can have A, which copies the text to a new line. You can have R, which copies the text to the, and then the instruction R file does the same. It copies the text to a new line when there's a match, but it copies the contents of the file indicated by file. Okay. So instruction W does the opposite of R. That is, the line will be appended to the indicated file. So what R does is, instead of so let's start with A. So what A does is it copies text indicated by text to a new line after the line with the file. So what R does is it copies the text indicated by so it copies the text indicated by okay, well, I'm not, this is my guess of what it does. So what I would guess, so A seems pretty self-explanatory. It's just if there's a match, then it duplicates the line with the match. But what I think R does is, if there's a match, then it duplicates the line of the match, but not just to the standard output, instead to a file that you specify. It writes that to a file. So let's play around with that. I'm going to finish reading this though. Instruction W does the opposite of R. That is, the line will be appended to the indicated file, and it does the opposite of R. How is that the opposite? Anyway, this is very unclear, and we've seen this material be very unclear before. So let's just clear it up quick by doing an exercise. And let's have the AI walk us through it. I just don't want to get off track here. So this is really confusing. Design a simple exercise that I can do in my Ubuntu lab to understand these concepts fully. Okay, so the first thing we're going to do is create a file named example.txt. I think we already got example.txt on here, but no, it looks like we don't. So I'm going to create that. Now I can do something like pretty cool. I can do t and then redirect it to example.txt. And now I can just dump it in right there and look at how, and then, oh, but then I'm, okay, so I'll remove example.txt. There we go. And then I can just dump this in like that. Hit a Control C. See how much like faster that is? Love it. Oh, it looks like I didn't get this last line though, so you have to have the new line after that. All right, that looks good to me. All right, looks good to me. So now the exercise steps for step. Oh God, oh no, please. Let me take a quick break. All right, I'm back and ready to go. So we're gonna go through the exercises now. So we've got that file. Let's cat that out. Okay, and then we're going to do the first exercise, which is to understand C removed instructions. So we're going to run the following command to replace any line containing the regex there. So, all right, I'm going to type it out just to, okay, so it's case insensitive, and then there's our encapsulation character. Here's our regular expression, which is comprised of atoms. And then all right, so there we go. Now if we cat out the file, so cat example.txt, we can see it's quite a bit different. We have removed for that line 4. Now it looks like there are some errors here. It did not match on 2. So let's see if I did it carefully enough. And it looks like I did. There's just an issue. So yeah, so I don't know why I was expecting to match this one, because if we this is a good lesson too. So what the match we're looking for is we're looking for it to match this here. So this line here, yeah, it matches there, but then what we're looking for is any character number of times and the number of 2. So we didn't have that here. There is a 2 in there, but this comes after it and not before, so it shouldn't be a match. So that's okay. It's still probably a better example than I could have come up with, or that's in the I mean, it doesn't get it right all the time, but it's close enough. All right, so step 2, let's try to understand the A text insertion. So we're going to run the following command to append the text after each line, removing the word containing the word removed. And I'll clear this up and I'll cat out the examples so it's a bit clearer. Okay, and now let's run the sed command. So it's sed-I. I believe that stands for case insensitive. And then there's a regular expression, so that's encapsulated. And then the command is going to be A. And now they're doing it in kind of a different syntax. They have this -A \text, which I'm kind of not used to seeing. But that's okay. Okay, and then we're going to cat example.txt. And now we've got removed, and we've got it on another line text. Yep, so that's good. Okay, now let's understand the R file instruction. So we're going to create a new file named additional.txt. So we can do that with t redirect additional.txt and paste that in there. And then we need a new line. Okay, so if we cat out that file, there we go. Run the following command to append the content of additional.txt after each line containing the word removed. Okay, so let's try that. So std-i removed. So we got to encapsulate that. R additional.txt. Okay, and then example.txt. Cat example.txt. There we go. And now we've got anytime it matched, so it matched on this line here because it's removed, it inserts the contents of the file. So you can see how powerful this will be for, like, you know, network engineering. Like, you know, this is good stuff. All right, so now let's understand the W file instruction. So I'm gonna clear this out, cat out example.txt. Okay, so run the following command to write each line containing the word removed to a new file containing removed_lines.txt. So std-n removed lines.txt. Okay, so notice we didn't have to create this file remove lines.txt in advance. That's because we created it now. So if we do a cat removed lines.txt, now that shows that the lines that said removed, we only had one, have been written to the new file. And there we go. So their contents look different than mine because there's an error. Sometimes there's errors. The AIs don't exactly get it right, but humans don't exactly get it right either. So as long as it's better than we could get, it's good in my book. So conclusion, through this exercise, you simulated each instruction using SED, a stream editor for filtering and transforming text in a Linux environment, and mic check 1, 2. Okay. You should now have a practical understanding of how each instruction works. Okay, and I believe I do. Okay, so in the example's case, every line with the substring matching the regular expression is infected by the instruction C, which replaces that line with the words with the word removed in uppercase. And then instruction A, and then text copies text indicated by text to a new line after the line with a match. We saw that. And then the instruction R does the same, but instead of copying the text you specify in the option like you do with A, it copies the contents of a file. And then W does the opposite of that. Instead of taking the contents of a file and putting it out onto the standard output, it takes the standard output and puts that into the contents of a file, and it appends it too. So by far the most used SED instruction is s/find/replace/, which is used to replace a match to the regular expression find with text indicated by replace. For example, the instruction s/hda/sda/ replaces a substring matching the literal regular expression HDA with SDA. Only the first match found in the line will be replaced unless the flag G is placed after the instruction, as in s/hda/sda/G. So that's important to know if you're trying to replace all your files that do a match. You won't get very far. In fact, you won't get past the very first one unless you include /G. A more realistic case study will help to illustrate SED's features. suppose a medical clinic. Oh, and I'll increase this. Okay, suppose a medical clinic wants to send text messages to its customers, reminding them of their scheduled appointments for the next day. A typical implementation scenario relies on a professional instant message service, which provides an API to access the system responsible for delivering the messages. These messages usually originate from the same system that runs the application controlling customers' appointments, triggered by a specific time of the day or some other event. In this hypothetical situation, the application could generate a file called appointments.csv containing tabulated data with all the appointments for the next day, then used by SED to render the text messages from a template file called template.txt. CSV files are a standard way of exporting data from database queries. So sample appointments could be given as followed. There we go. So cat appointments.txt, name, time, phone, and there we go. That's an example appointment. The first line holds the labels for each column, which will be used to match the tags inside the sample template file. So there we go. Cat template.txt, hey, and then it plugs in the name. Don't forget your appointment tomorrow at, and then plugs in the time. The less than and greater than signs were put around the labels just to help identify them as tags. The following bash script parses all in-queued appointments using template.txt as the message template. Okay, so here's an example of what that message template might look like. Hey, and then to show that it's a variable that gets plugged in. Don't forget your appointment tomorrow at, and then you can show them the time, the location, whatever you would like. So here's a bash script. We can see the shebang at the top, which lets Linux know that if you change it to an executable, it will know what to use to execute the file. It'll use bash. Okay, so here we go. There's the template file. Yep, and then SED. So you can see, like, this is like why Python was made. This gets pretty unruly. So this is like a good thing to learn about for, like, why Python? Why is there Python? Well, it's because look at this script. In fact, let's do this. Let's do this as an exercise. So rewrite this script using Python 3. Do this as part of a larger intention, which is to educate people on what is Pythonic and what is not, and as such, why Python 3 is such a powerful tool as compared to bash.
Readability in its powerful standard library. Here's how you can write a Python script that mimics the behavior of a bash script. The script is generally more readable and maintainable than the equivalent bash script, thanks to Python's clear syntax and powerful standard library. To execute the curl commands from within the Python script, you can replace the print curl_command line with a called OS. System, curl_command, after importing the OS module at the start of your script. However, in a more Pythonic approach, you might use a library like request to send the HTTP requests directly from Python, rather than spawning external curl processes. This would make your script even more efficient and Pythonic, but it would require installing an external package with pip install requests.
Yeah, so like, print out the bash script in the most clean way possible, and then print out the Python script afterwards and go through each line and explain why the Python script looks better.
Certainly. Here's a cleaner representation of your bash script followed by the Python script with a detailed explanation of each line.
See what I mean? It's like looping over. It's such a long line.
Bash script.
Yeah, see this? So this is a really good. And look at this, all the lines. Like most of these are just comments.
Python script.
Like nothing extends out too far. You don't get all this crazy syntax. What does that
Detailed
even
explanation
mean?
importing CSV module Python copy code import CSV and Python. We start by importing the CSV module, part of Python's rich standard library, which will allow us to easily and reliably read CSV files. Bash doesn't have a built-in way to handle CSV files properly, leading to more complex and error-prone code. Reading the template Python copy code with open template. txt art as f, template equals f. Read. Here we read the content of template. txt using a with statement which automatically handles file closing, ensuring cleaner and safer code compared to bash which doesn't automatically close file descriptors, potentially leading to resource leaks.
Yeah, see.
Reading the CSV file Python copy code with open appointments. CSV art as f. Reader equals CSV. Reader, f, headers equals next, reader, rows equals list, reader. We again use a with statement to read the CSV file. We get the headers and rows in just 3 lines of Python code, whereas in bash it took multiple commands and was more prone to errors due to CSV formatting issues. Looping through each row Python copy code for row and rows. MSG equals template Pythons for loop iterates over a list of rows, which is more intuitive and readable compared to bash's index-based loop. Replacing tags with values Python copy code for header, value and zip, headers, row. MSG equals MSG. Replace f less than, header, greater than, value. We use a nested loop in the SDR.
Okay, so anyway, you can see, so the conclusion, the Python script is generally more readable and maintainable thanks to Python's clear syntax and powerful standard library modules, which help in writing concise and less error-prone code. It also allows for safer file handling and more intuitive loops and string manipulations, showcasing why Python is often preferred for tasks involving file, input-output, and string processing. So this is a really good precursor to learning Python, because you can really see like, oh, this, and you can even use this in the real world and be like, oh, this is just such a nightmare to get right. If only there was something better. Well, guess what there is? That's Python. So an actual production script would also handle authentication, error checking, and logging, but the example has basic functionality to start with. The first instructions executed by SCD are applied only to the first line. The address 1 in see what I mean? To remove the leading and trailing quotes. So we've got that and that. That's how we're doing it. And this isn't that bad because we can see one is it's encapsulated in the regular expression. So yeah. And to replace field separators with a new line character, which we are seeing here. Only the first line is needed for loading column names, so non-matching lines will be suppressed by option -n, requiring flag P to be placed after the last SED command to print the matching file. The tags are then stored in the tags variable as a bash array. Another bash array variable is created by the command mapfile to store the lines containing the appointments in the array variable rows. Alright, so a for loop is employed to process each appointment line found in the rows, and we can see that much more clearly happening here. So here, see how clear it is to know that there's a for loop like that? And then here, I guess it's not that difficult to see that there's a for loop occurring here. But just for row in rows, and I don't know. Then quotes and separators in the appointment. The appointment is in variable like that. used as a here string. So remember the here strings? Those are standard input past, yeah, standard input basically, are replaced by SED, similarly to the commands used to load the tags. The separated values for the appointment are then stored in the array variable vals, where array subscripts 0, 1, and 2 correspond to values for name, time, and phone. Finally, a nested for loop walks through the tags array and replaces each tag found in the template with its corresponding value in vals. The MSG variable holds a copy of the rendered template, updated by the substitution command, which is very Pythonic there, on every loop passed through tags. This results in a rendered message like, hey, and then we filled in with Carol, don't forget your appointment tomorrow at 11 a.m. The rendered message can then be sent as a parameter through a HTTP request with curl as a mail message or any similar method, or any other similar method. So it looks like we got a lot of reading to go. I kind of would like to get through. Let's see what the time is. If the time's past an hour, oh, it's at 56 minutes. I'm tempted to just cut it and then do the rest in another video. You know what? I think I'm gonna do that. So I'm gonna cut the video here, and then finish all of this up in a part 2. So, I'm tempted to just pause it and come back and close it out in one video, but I just feel like this might take longer than I realize. It'll take at least a half an hour. Alright, so yep, that's it for this video, which is lesson 2, part 1. So thanks for watching, and see you in the next one.